From a fire safety standpoint, there is a significant difference between a grounded receptacle and an ungrounded ground fault circuit interrupter, or GFCI, receptacle. A grounded receptacle protects against electrical fires caused by ground faults. Current has a safe path to flow back to the electrical panel in the event of a ground fault, reducing the risk of electrical fires. It also provides a low resistance path for fault current to flow. The ground wire in the receptacle connects to the ground rod outside the building, creating a direct and low resistance path for fault current to follow, ensuring it does not flow through people or equipment. An ungrounded GFCI receptacle protects against electrical shocks but not fire. A GFCI receptacle only protects against electrical shocks by sensing imbalances in current flow and tripping if it detects a fault. It does not provide a low resistance path for fault current to flow. It may not prevent electrical fires. In the event of a ground fault where current cannot flow back to the panel through a grounding conductor, the fault current may flow through people or equipment, increasing the risk of fire. Therefore, while an ungrounded GFCI receptacle may provide electrical shock protection, it does not offer the same level of fire protection as a properly grounded receptacle. It is always recommended to ensure that receptacles are properly grounded, especially in areas where electrical fires could pose a significant hazard. A grounded receptacle has a connection to earth, usually through a grounding wire connected to a ground rod or a metal water pipe entering a building. This connection provides a low impedance path for fault current to flow back to the source, typically the electrical panel. This low impedance path is crucial for safety. When a ground fault occurs, such as when a live wire comes into contact with a metal enclosure, the fault current flows through the grounding path. This high current causes the circuit breaker to trip quickly, interrupting the power and preventing a dangerous voltage from being present on the enclosure. This rapid clearing of the fault minimizes the risk of electric shock and fire. In contrast, an ungrounded receptacle does not have this direct connection to earth. It relies solely on the GFCI to detect imbalances in current flow. While the GFCI is effective at preventing electric shock by quickly interrupting the circuit when a ground fault is detected, it does not provide a low impedance path for fault current to flow. In the event of a ground fault, the current may flow through other paths, such as through a person touching the faulty equipment before the GFCI trips. This can still result in a dangerous electric shock, although the GFCI will significantly reduce the duration and severity of the shock. Furthermore, the absence of a grounding path can increase the risk of fire. Without a low impedance path, the fault current may not be high enough to trip the circuit breaker quickly. This can cause the wiring and equipment to overheat, potentially leading to a fire. The grounding system also plays a vital role in preventing the buildup of static electricity. Static electricity can accumulate on ungrounded equipment, which can be a nuisance and, in some cases, a fire hazard. The grounding system provides a path for this static electricity to dissipate safely to the earth. Electrical codes typically require grounding for all electrical systems and equipment. However, there are some exceptions, such as in older homes where grounding is not present. In these cases, GFCI protection is often permitted as an alternative. However, it is important to understand that GFCI protection is not a substitute for grounding. While GFCI protection can significantly reduce the risk of electric shock, it does not provide the same level of fire protection as a properly grounded system. If you are considering installing ungrounded receptacles with GFCI protection, it is important to consult with a qualified electrician. The electrician can assess your specific situation and determine the best course of action to ensure the safety of your electrical system. Firstly, consider the age of the wiring. Older homes may not have grounding wires installed. Secondly, consider the presence of GFCI protection. GFCI protection can significantly reduce the risk of electric shock. Thirdly, consider the type of equipment being used. Certain types of equipment, such as computers and medical equipment, require grounding for proper operation. In addition to grounding, there are other measures you can take to improve the fire safety of your electrical system. These include regularly inspecting your wiring and equipment for damage, replacing any damaged wiring or equipment, and installing arc fault circuit interrupters, or RFCIs. RFCIs are similar to GFCIs, but they are designed to detect arc faults, which are a common cause of electrical fires. Arc faults occur when there is an unintended arc of electricity between two conductors. This can happen when wiring is damaged or when connections are loose. RFCIs can detect these arc faults and interrupt the circuit, preventing a fire. Grounding provides a low impedance path for fault current to flow back to the source, which causes the circuit breaker to trip quickly. This rapid clearing of the fault minimizes the risk of electric shock and fire. Secondly, grounding prevents the buildup of static electricity. Static electricity can accumulate on non-grounded equipment, which can be a nuisance and, in some cases, a fire hazard. The grounding system provides a path for the static electricity to dissipate safely to the earth. Thirdly, grounding helps to stabilize voltage. A stable voltage is important for the proper operation of electrical equipment. The grounding system helps to maintain a stable voltage by providing a reference point for the electrical system. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. These requirements are designed to ensure the safety of people and property. The NEC specifies the types of grounding conductors that are permitted, the size of grounding conductors, and the methods for connecting grounding conductors. The NEC also requires that all electrical equipment be properly grounded. This includes receptacles, lighting fixtures, appliances, and other electrical equipment. There are several different types of grounding systems. The most common type of grounding system is the equipment grounding system. The equipment grounding system connects the metal enclosures of electrical equipment to the earth. This provides a low impedance path for fault current to flow back to the source. Another type of grounding system is the system grounding system. The system grounding system connects the neutral conductor of the electrical system to the earth. This helps to stabilize voltage and prevent the buildup of static electricity. The grounding electrode system is the portion of the grounding system that is in direct contact with the earth. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode system must be sized and installed in accordance with the NEC. Grounding is an essential part of electrical safety. It provides a low impedance path for fault current to flow back to the source, which causes the circuit breaker to trip quickly. It also prevents the buildup of static electricity and helps to stabilize voltage. All electrical systems and equipment should be properly grounded in accordance with the NEC. An ungrounded electrical system, also known as an isolated system, does not have a direct connection to earth. While less common, these systems are used in specific applications where isolation from ground is beneficial. Examples include certain industrial processes, medical equipment, and some critical power systems. In an ungrounded system, a ground fault does not immediately trip a circuit breaker. Instead, the first ground fault creates a condition where the entire system voltage is present in the faulted conductor with respect to ground. This situation doesn't interrupt power but presents a heightened risk of insulation breakdown and a second ground fault. A second ground fault on a different phase will create a short circuit, causing a breaker to trip and interrupting power. Ungrounded systems are often equipped with ground fault detectors that signal the presence of a ground fault without immediately shutting down the system. This allows for a controlled shutdown and repair, minimizing disruption in critical applications. The advantage of an ungrounded system is its ability to continue operating during a single ground fault. This is crucial in applications where an immediate shutdown could have severe consequences. However, the risk of a second fault leading to a complete shutdown and the increased stress on insulation necessitate careful monitoring and maintenance. In contrast to grounded systems where the fault current has a clear path back to the source, in an ungrounded system the fault current is limited by the capacitance of the system to ground. This capacitance is distributed throughout the wiring and equipment and provides a path for the fault current to flow. However, the impedance of this path is much higher than in a grounded system, which limits the magnitude of the fault current. While an ungrounded system can continue to operate with a single ground fault, it is essential to locate and repair the fault as soon as possible to prevent a second fault from occurring. Regular installation testing and monitoring of ground fault detectors are critical maintenance practices for ungrounded systems. The National Electrical Code (NEC) provides guidelines for both grounded and ungrounded systems, specifying the conditions under which each type of system is permitted. The choice between a grounded and ungrounded system depends on the specific application and the priorities of safety, reliability, and operational continuity. Grounded systems are generally preferred for their safety features, while ungrounded systems offer increased operational reliability in certain critical applications. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock by detecting imbalances in current flow. When a GFCI detects that current is leaking to ground, it quickly interrupts the circuit, preventing a dangerous shock. GFCIs work by monitoring the current flowing through the hot and neutral conductors. Under normal conditions, the current flowing through these conductors should be equal. However, if current is leaking to ground, there will be an imbalance in the current flow. The GFCI detects this imbalance and trips the circuit. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electric shock. They are an important safety device that can help to protect people from serious injury or death. Arc fault circuit interrupters, or GFCIs, are designed to protect against electrical fires by detecting arc faults. Arc faults are dangerous electrical conditions that can occur when there is a break in the insulation of a wire or a loose connection. When an arc fault occurs, it can generate heat that can ignite nearby materials, leading to a fire. GFCIs work by monitoring the electrical current for characteristics that are indicative of an arc fault. When an arc fault is detected, the GFCI trips the circuit, preventing a fire. GFCIs are required in many locations, such as bedrooms and living rooms, where there is a high risk of electrical fires. They are an important safety device that can help to protect people and property from fire. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges are sudden increases in voltage that can damage or destroy electrical equipment. Voltage surges can be caused by lightning strikes, power grid switching, and other events. SPD work by diverting the surge current away from the protected equipment. When a voltage surge occurs, the SPD provides a path for the surge current to flow to ground, preventing it from reaching the protected equipment. SPD are available in a variety of types and sizes. They can be installed at the service entrance of a building or at individual pieces of equipment. SPD are an important safety device that can help to protect electrical equipment from damage. Regular electrical inspections are an important part of maintaining a safe electrical system. During an electrical inspection, a qualified electrician will inspect the wiring, equipment, and other components of the electrical system to identify any potential hazards. The electrician will also test the operation of safety devices, such as GFCIs and GFCIs. Regular electrical inspections can help to identify and correct electrical problems before they cause a fire or electric shock. It is recommended to have an electrical inspection performed every 3 to 5 years. If you are buying or selling a home, it is also a good idea to have an electrical inspection performed. This can help to identify any potential electrical problems that may need to be addressed before the sale is completed. When choosing an electrician, it is important to select a qualified and experienced professional. Ask for references and check the electrician's credentials. Make sure the electrician is licensed and insured. A qualified electrician will be able to properly inspect, repair, and install electrical equipment. They will also be able to provide advice on how to improve the safety and efficiency of your electrical system. In summary, grounding is crucial for fire safety as it provides a low impedance path for fault currents, enabling quick breaker tripping and minimizing fire hazards. While ungrounded GFCI receptacles offer shock protection, they do not provide the same level of fire protection as grounded receptacles. Therefore, ensuring proper grounding, supplemented by GFCIs and GFCIs, and regular electrical inspections are essential for comprehensive electrical safety.